All right. So thank you and welcome, and thank you for joining me today. My name is W Morse, and today I'll be presenting the work that I did during my master's. The work is titled Critical Heat Flux and the Dryout of Liquid Film in Two-Phase Annular Flow. So the presentation is broken into 4 sections. We'll start in the obvious place with the introduction. In this section, I'll provide a description of the work that we did during this research and then some of the goals that we had while performing this research. Next, then I'll provide a brief literature review before moving into the experimental section. So in flow boiling systems, energy is transferred from the walls of a heated channel to a saturated fluid by a combination of forced convection and evaporation. The saturated fluid progresses through a series of flow regimes as vapor quality is increased. The process is visualized. I'm going to use there we go. That's the first one. All right, so I'm going to use the laser here. It's going to be a little clunky, but the process is visualized as going from the left to the right-hand side of this figure with increasing vapor quality. The heat transfer coefficient, abbreviated as HTC, is the proportionality constant that relates the heat flux to the temperature difference between the heated surface and the saturated fluid. A qualitative description of the heat transfer coefficient, HTC, as a function of vapor quality is shown on the bottom part of this figure here. The HTC increases and reaches a maximum value in the annular regime, which is the focus of the current study. Annular flow is characterized by a vapor core, a thin liquid film on the wall, and liquid droplets entrained within the core. Shear at the liquid-vapor interface drives the liquid film flow along the heated surface. In general, with increasing vapor quality, there is a decrease in the local film thickness and an increase in the local heat transfer coefficient. A very important phenomenon that occurs in flow boiling is the onset of the boiling crisis, and that's shown in red in the far right of this figure. So the boiling crisis is characterized by a significant reduction in the heat transfer coefficient to the fluid and an increase in surface temperature. The boiling crisis here and the reduction in HTC that ensues is associated with the loss of liquid film, and this is called dryout. So the video shown here captures the dryout event occurring within our test section. The fluid moves from the bottom to the top of the screen, and we are actually looking through the heated surface. I'll explain how we heat the walls a little bit later. I'm showing this video for a couple of reasons. First, the video actually provides some physical context of what we're talking about. But more importantly, the video shows that a local position does not immediately reach dryout completion, or a point at which the liquid is no longer able to wet the surface. In the video, we can see that the liquid film dries out, the dry region spreads, and then a liquid wave swiftly moves from the bottom to the top of the screen, re-wetting the surface. In reality, many of these dryout events occur during the onset of the boiling crisis. So what does this mean about the heat transfer? How does the HTC respond over many of these dryout events? Characterizing the dryout process and understanding the local conditions that lead to dryout was a major part of this research. So for annular flows, the critical flow conditions are the conditions at which the maximum HTC occurs, and this is indicated here as CHF. The value of the heat flux at which the local maximum in HTC occurs is called the critical heat flux, which is abbreviated as CHF. The local vapor quality at the max heat transfer coefficient is referred to as the critical vapor quality, which is labeled here as X sub crit. And it is necessary to define the nomenclature how I've used it in this work, because the nomenclature in literature is actually inconsistent among authors. So in this slide, I've gathered examples of how other authors have described critical heat flux. And keep in mind that critical heat flux is indeed a heat flux, and therefore it has a nominal value. It is not some abstract idea or anything more complicated than that. So I've broken the table down into 3 groups. The first group, each of the authors provide essentially the same qualitative description. In the second group, each of the authors provide their own qualitative description. However, none of these definitions is actually describing a heat flux. The third group of authors present quantitative descriptions. However, neither definition in group 3 can be applied universally. So as you see, there is little agreement in the literature on the definition of critical heat flux. Even papers from the same lab, Tolmy's lab, who is one of the leading experts in our field, cannot seem to agree on a single definition. But the quantitative description that I've provided and that we'll use throughout this work agrees with the qualitative description provided by the authors of Group 1. So I've consolidated the remainder of our literature review into the following table. Time average data for heat transfer coefficient, vapor quality, and heat flux have been provided by many sources in literature. Many correlations have been presented for CHF for varying fluids and flow orientations. Visualization of the dryout process has been presented in only 3 works. However, none of these observations were made through the heated surface. Only Borhani and Tomi have presented time average conditions relating to dryout characteristics. However, the authors made their observation using high-speed video and were therefore very limited in their length of their data sets. And to my knowledge, there exists no literature containing time-resolved measurements during dryout conditions. So this is one big gap in the literature that we would like to fill. All right, so next we'll move into the experimental section. I'll start by first providing a description of our apparatus and discuss some of the measurements that we make. Then I'll provide a description of the two-phase experimental procedure that we use using an example data set. So here's a full schematic of the MFVal annular flow facility. The working fluid in the flow loop is R245FA, which is a low-pressure refrigerant that possesses fluid properties similar to that of high-pressure steam. Two-phase flow is generated by mixing subcooled liquid and superheated vapor. So starting from the storage tank, fluid is driven through 2 circuits, one for the vapor and one for the liquid. The 2 circuits meet here in the mixing tee. Superheated vapor is mixed with subcooled liquid to form a two-phase mixture. After the mixing tee, the fluid flows upward through a well-insulated channel that provides enough length for the flow to become fully developed. Once the flow is fully developed, it enters our test section at the inlet, and the test section is seen here. We have verified that the heat loss to the surroundings from the development section is negligible, and therefore the enthalpy at the inlet of the test section is equal to the enthalpy at the outlet of the mixing tee. The inlet vapor quality can be calculated using the inlet enthalpy and the enthalpies of saturated liquid and vapor phases evaluated at the inlet pressure of the test section. So next for the actual test section itself, it's illustrated here on the right. So the test section consists of an Ultem plastic frame, aluminum plates, and glass windows. And the glass windows are coated with a conductive oxide coating. An electrical current is applied to the conductive coating, allowing for the inner wall of the test section to be heated. So here's an actual picture of the apparatus taken from underneath the optical setup. The flow channel cross-section is 36 millimeters by 12 millimeters, which provides a hydraulic diameter of 18 millimeters, and the heated length of the test section is equal to the length of the windows, which is 525 millimeters. Process conditions such as temperature, pressure, and differential pressure are all measured within the test section, as shown on the diagram. Liquid film thickness is also measured using a non-invasive optical technique at the location noted on the figure. In addition, high-speed video is collected at the same location by just simply removing the light diffuser. Using a laser reflectance technique, which is indicated by LR on the figure here, we are able to actually measure the state of the wall. I lost my mouse now. Hold on, sorry guys. We are able to measure the state of the wall as wet or dry at the local position of the measurement. So the state of the wall is measured using this laser technique that is dependent on the index of refraction of the fluid at the interface. The technique is capable of measuring temperature at the interface as well, and therefore the apparatus is actually a little bit more complicated than it needs to be for this measurement. On the left is a schematic of the laser reflectance apparatus, which includes polarizers, lasers, diodes, and then eventually the test section is shown here. The figure on the right displays the laser path through the prism, through the glass, to the interface, and then eventually back out through the prism and to the receiving diode. At the glass fluid interface, a portion of the beam is reflected and the rest is transmitted into the refrigerant. And then after passing through a prism and a mirror, the intensity of the reflected beam is measured by the photodiode at the outlet. The intensity ratio is the intensity leaving the test section divided by the intensity entering the test section. And the difference in index of refraction between liquid and vapor R245 FA is such that with an appropriate angle, most of the incident laser beam is transmitted into the liquid film. And for the same angle, most of the light is reflected when vapor is in contact with the window. When the liquid dries out in the measurement location, there's a sudden change in the index of refraction of the fluid at the interface. This sudden change leads to a large change in the measured intensity ratio when the wall transitions from wet to dry. This is captured here in the figure. So multiple dryout events can be seen in this figure here. Here the data labeled with blue markers indicate a wet state at the wall, and the red markers indicate a dry state. So moving forward, when we look at this intensity ratio signal, we should remember that big spikes indicate dryout event is occurring, or dryout is occurring in the test section. With this instantaneous indication of wet or dry conditions, a temporally averaged dry time fraction, F sub dry, can be calculated using the cumulative dry time divided by the total time. The extent of individual dryout events, as well as the time between dryout events, is also easily recorded using this intensity ratio signal. So now we're going to talk about how heat is input into our system. This is a simplified diagram showing how the heat is input into the working fluid. Electrical power is converted into thermal energy within the FTO coating at the inner surface of the wall. That's shown here in red. A portion of the heat is transferred to the working fluid, this portion, and the rest is lost to the surroundings, and that's shown here. The amount of heat lost to the surroundings must be accurately characterized in order to accurately estimate the heat input into the working fluid. So, in order to characterize the heat losses, a thermal resistance network representing the heat transfer circuit of the test section was made and is shown here. Heat enters the circuit through the window coating here, and the portion of the applied heat that moves to the right enters the working fluid. The resistance associated with convection into the two-phase mixture is provided with this equation. Little h, which is the local heat transfer coefficient, is the quantity we actually want to measure. Therefore, we must be able to accurately calculate the remaining resistances. The heat that's lost to the surroundings goes to the left from center of the schematic here. The resistance associated with conducting through the glass is calculated using this equation, which contains all known quantities. The resistance associated with convecting to the ambient surroundings is shown here. So the external heat transfer coefficient due to natural convection is labeled H sub EXT and circled here in red, and this is an unknown term. The second route for heat to be lost is through the ULTEM section here, and the conduction through the ULTEM and eventually natural convection from the surface of the ULTEM to the surroundings is lumped into one resistance labeled R sub TS. So the two unknown quantities, R sub TS and H sub XT, were obtained through a regression of data under single-phase conditions. So we have verified that the estimated values of heat input and measured values of heat input agree with one another. Now that we are able to characterize R sub TS and H sub EXT, we can accurately measure H. So using the effective heat input into the refrigerant, the local specific enthalpy at the outlet of the test section is calculated. The local specific enthalpy is then used to find the local vapor quality. Finally, the local heat transfer coefficient, little h, is calculated as the effective heat flux divided by the difference in wall and saturation temperatures. All right, so in the next few slides, I'm going to show you figures of time traces of the signals used to identify the dryout characteristics of the flow within our test section. These are a little bit daunting, but hopefully together we can break them down into something that makes sense. So the black line here indicates the effective heat flux. The red line here indicates the outer wall temperature, so the exterior wall of the test section. The blue line here indicates the saturation temperature. And the orange data here is the intensity ratio that we looked at earlier. So the spikes, again, indicate dryout has occurred. So prior to collecting data, the flow loop is allowed to reach a steady state condition without any heat input into the test section. In this case, heating begins at around 80 seconds and is indicated here as the spike in intensity rate, or as the spike in the step increase in heat flux, and then a response in the outer wall temperature. So after a few seconds, the exterior wall temperature reaches a new equilibrium, and then the heat is increased. This process is repeated until the heating power reaches a level at which dryout is actually observed. So at approximately 550 seconds here, the first indication of a dryout event occurs within our test section. As heating power is increased further, more dryout events are detected between 650 and 675 seconds. The presence of the dryout events can be seen more clearly in close-ups of the time trace. So let's take a look at detail 1. Here, we have a fixed effective heat flux of 18 kilowatts per meter squared. And the temperature of the exterior wall remains constant, even though we have dryout events observed here, here, and here. So this indicates that even though we have dryout events occurring, the time average local heat transfer coefficient at the wall is largely unaffected by these first dryout events. So at this point, the heat flux is further increased from detail 1, and the behavior that ensues is captured in detail 2. So in detail 2, the effective heat flux has been increased, which has caused an increase in frequency and duration of the dryout events. The exterior wall temperature increases, but only slightly, about 1 degree Celsius, before it reaches the new equilibrium temperature. The effective heat flux is further increased at around 765 seconds, causing many more dryout events and causing the wall temperature to rise about 5 degrees Celsius. That can be seen here. This corresponds to the first significant reduction in time average heat transfer coefficient. Dryout events occur much more frequently, and the spacing between the dryout events has decreased. So finally, at approximately 850 seconds, the supplied heat flux is increased to 22 kilowatts per meter squared, which is an increase of less than 5% from the previous value. And this small increase in heating power results in a large reduction in the heat transfer coefficient, which is seen here as a runaway temperature condition. So the red line indicates the exterior wall temperature, and as you can see, it increases, and it does not look like it is going to reach a new steady state anytime soon. So this behavior is consistent with the boiling crisis and results from exceeding the critical heat flux. So at this point, the temperature in these runaway temperature conditions, the experiment is concluded before the window temperature reaches a level that could actually damage our apparatus. All right, so now we're going to actually get into the results section. So the following slides are going to present the experimental results from our study. First, we're going to look at time average data for process conditions. And next, we're going to look at some time average data that relates to the dryout. And then finally, we're going to use direct observation to look at high-speed video and then look at some dryout statistics as well. So if I had to boil my thesis or my presentation down to a few figures, this would be probably one of three figures, one of the three main figures. So the onset of dryout happens before the start of the boiling crisis. And in this figure, the local heat transfer coefficient and the F dry are shown as a function of local vapor quality. So initially in this region here, with increasing vapor quality, there's no real change in the heat transfer coefficient. The measured F dry here, so the measured temporal dry fraction here, is 0, and so it's just not shown on the figure. At vapor qualities for which dryout events are first recorded in this region here, there is an increase in the measured heat transfer coefficient. You can also see that F dry becomes non-zero and starts to increase in this region here. This has been labeled the intermittent dryout region. The local maximum in HTC occurs here on the border of the intermittent dryout region and the boiling crisis region, and further increase in vapor quality leads to a large reduction in the heat transfer coefficient. Characteristics of this data set are representative of all the data collected in this work, and if you are particularly interested in taking a look at that, you could request a copy of my thesis. So in this figure, experimental data for critical heat flux is shown as a function of local vapor quality for mass fluxes of 130, 150, and 170 kilograms per meter squared second. So for the mass fluxes investigated in this work, there was no significant effect on the mass flux on the value of CHF. So in this region, vapor quality dominates over mass flux. And this is to be expected based on experimental data performed for mass fluxes less than the mass flux region we were looking at, and also for more. And so there is a change in behavior in the region that we're looking at. So the predictions from correlations of Ong and Tomi, shown here in black, Shah is shown here, and Voitan. And the correlation contours were calculated using the average mass flux, so G is equal to 150. As you can see, there's a change in slope that occurs in the experimental data around a vapor quality of 0.95. This change in slope suggests a change in regime or a change in behavior, and this is captured in the model of Ong and Tomi, and also in that of Shah and Voitan. However, it's less obvious. All right, so next we're going to compare our experimental data to existing correlations for critical heat flux, which is on the left, and for critical vapor quality, which is on the right. So the three models that we looked at on the previous plot, that of Ong and Tomi, Voitan, and Shah, provide the best estimate for the experimental critical heat flux. For critical vapor quality, the correlations that provide the closest estimate, so here, fail to reflect the trend of the data. However, the correlations that best reflect the data trend, here and here, fail to accurately estimate the absolute value of the experimental critical vapor quality. The lack of good agreement between the different correlations in the literature demonstrates the need for a more detailed description of the boiling crisis phenomena based on local time-resolved measurements. So it was shown earlier that dryout events occur prior to a decrease in heat transfer and therefore prior to the critical heat flux. So this figure shows the difference between dryout conditions and critical flow conditions for a single mass flux of G is equal to 150 kilograms per meter squared. The heat flux at which dryout occurs is called the dryout heat flux and is labeled here as DHF. The red and black dotted lines have been drawn for a visual guide. So in between the black and red, there is an increase in heat transfer coefficient, even though you're intermittently drying out. The slope of the DHF is similar to that of the CHF. And just a note on uncertainty. So error bars are actually covered by the data points here. If you guys want to talk more about uncertainty, we can after, but I was going to save that for bonus material. So in an effort to compare heat transfer coefficient for different mass flux values, a normalized heat transfer coefficient, which is labeled here as big H, is calculated. A weighted normalized heat transfer coefficient, H subweighted, is also calculated. The big H subweighted represents what the HTC would do if it simply decayed from a two-phase value to a single-phase value linearly with F sub dry. So here we have the normalized heat transfer coefficient and the normalized weighted heat transfer coefficient are shown as a function of dry time. The weighted average approach is shown as the black dotted line, and you can see that it fails to accurately predict what the heat transfer coefficient is doing during dryout. So with increasing mass flux, the maximum value in the normalized heat transfer coefficient tends to decrease slightly, but otherwise for the range of mass fluxes investigated, there's little effect on the normalized heat transfer coefficient. So at F dry approximately equal to 0.05, the normalized heat transfer coefficient reaches a maximum value and is increased between 10 and 25% from its original value. So that means at this point, when the heat transfer or when the wall was fully wet, to this point, where now we're dry about 5% of the time, the heat transfer coefficient has increased between 10 and 25% of the time. Further into the boiling crisis, increasing F dry, there's a large reduction in the normalized heat transfer coefficient, and it approaches zero as the normalized heat transfer coefficient, or as the local heat transfer coefficient, approaches the value for the single phase vapor. So once H approaches HV, this term becomes zero, and we end up over here. So in this figure, the same data are shown, but without differentiating between mass fluxes and on a logarithmic scale. So as you can see here, in the first moments of dryout, the heat transfer coefficient is largely unaffected. However, once there is, a small amount of dryout, so between 1 and 5%, there's an increase between 10 and 25% in your heat transfer coefficient. Once you've exceeded this 10 to the negative 1 value, the local heat transfer coefficient nosedives, and the weighted average, again, fails to accurately characterize what's happening with the heat transfer coefficient. All right, so now we're going to look at some statistics that we gathered using the laser reflectance technique. So here, the the duration of dryout events is shown for increasing dry fraction. For low dry fractions, shown here, the length of dryout events is very short. The window dries and immediately is re-wet. However, as we increase dry fraction, so going from left to right and then down from left to right, the distribution of the dryout events, so the duration of these dryout events, has widened. And so any one dryout event will now take a longer time to be re-wet prior than it did at the very beginning. All right, and so this is also, if I was going to narrow my thesis down to just a few plots, this would certainly be in it. So this is one of the most interesting results that we observed through this research. The figure shows the time between dryout events, and this can also be thought of as the time the window spends wet. So at low dry fractions, the time between dryout events is randomly spaced. There's no real pattern to when the dryout events occur. But as we get further into the boiling crisis and dryout events are occurring more frequently, the window is dry more frequently, there's a peak that emerges in the signal at around 0.25 seconds. So once dryout events are occurring cyclically in your test section or in your system, there is a characteristic dry time that occurs. So it's like clockwork. Every 0.25 seconds, this window is drying out. And so for large F dry, this is a characteristic dry time. All right, so now we're going to look at a video that captures a dryout event and a subsequent re-wetting event within our test section. The entire video spans about 375 milliseconds, and the playback rate is 20 frames per second. So the flow conditions were provided. The fluid flows from the bottom to the top of the field of view. At the beginning of this clip, the liquid vapor interface possesses surface features such as ripples, waves, droplet detachment, and deposition. After a short time, however, the surface features on the liquid vapor interface begin to diminish, and the interface becomes very smooth. In the local position highlighted here, the surface features have completely vanished. This also happens to be the location where the very first dry region forms. A second dry region forms, and the two dry regions coalesce into a single dry region which grows quickly in the streamwise direction. At this point, nearly the entire heated surface is dry. The blue line drawn on the bottom here indicates the arrival of a wetting front. At this point, the frame rate is decreased to 6 frames per second to account for the difference in time scales between the dryout and re-wetting events. So the wetting front comes from the bottom of the screen to the top of the screen, and you'll see it eventually stalls, and it no longer possesses the necessary momentum to move the wetting front downstream. There's a blue dotted line, and this indicates the presence of a thick film wave advancing towards the stalled wetting front. The wave catches up with the wetting front and now provides the necessary momentum to continue the re-wetting process. The liquid film is now able to re-wet the surface. So this video shows the time scales for the dryout event to occur and the re-wetting event to occur are significantly different. The re-wetting event happens very quickly and the dryout event takes some time. So through this analysis, we've observed that the velocity of the fluid in the wake of a wave is also small relative to that of a disturbance wave, and that the re-wetting process occurs on timescales that are much smaller than the drying process. Furthermore, through liquid film thickness data, which I don't have time to show you today, it was observed that during intermittent dryout, the liquid film was on the order of 30 to 40 microns, and the viscous sublayer is estimated to be about 25 microns. So any perturbations at the interface could therefore expose the viscous sublayer, the local position to the vapor core. The increased contribution from the viscous forces near the wall would dampen the propagation of surface ripples, causing the liquid film to become very, very smooth, which we observed in the video. As the liquid film becomes very smooth, there's less interfacial shear between the vapor and liquid, and this further reduces the velocity of the liquid film. If the liquid film were then to assume to be stationary, then the time required to vaporize the film could be estimated as the product of the liquid film thickness times the density times the enthalpy of vaporization, all divided by the effective heat flux. So these are 3 data sets that we took that, again, I don't have time to go through today, but these are 3 data sets for varying conditions with varying vapor quality and varying liquid film thickness. But the estimated dryout times based on the data sets are provided here as 0.18 seconds, 0.25 seconds, and 0.31 seconds. So this agrees well with the characteristic dryout time that we observed in the PDFs. The good agreement, along with the direct observation of the liquid film, provide good evidence that the film in the wake of the wave is nearly stagnant. So some of the conclusions that I have for you. So again, if we were going to sum this down into a couple slides or a couple plots, CHF versus DHF, so being able to identify when the film dries out versus when you actually reach critical flow conditions, the dryout and rewetting mechanism that we observed during the high-speed video, and also the dryout statistics for various F-dry. So like I said, no other authors have been able to provide dryout statistics because most of these experiments are done in facilities that have metal channels or walls that you're not able to see through. All right, and so finally, we have an updated version of our regime map, and this now includes the intermittent dryout regime and the dryout conditions, DHF here, and we have our dryout vapor quality here, are indicated in their appropriate position. So the behavior of the heat transfer coefficient during dryout is perhaps better described using F sub dry rather than the local vapor quality. We observed only a 1% change in local vapor quality between dryout and critical conditions. However, F sub dry gives you quite a range to characterize the heat transfer coefficient behavior. So that concludes everything I have for today. I just wanted to say thank you all for joining me. Thanks especially to Greg, Argenthal, and Dressler, who are my advisors, for putting up with me and for always going to bat for me and allowing me this opportunity to work here. To previous MF Valors, such as like Mark Rodarte, who built this facility, Brian Faring, who helped, and current MF Valors, Jason, and all the undergrads. I also wanted to say thank you to Evan and Luis, our sponsors, who have been very supportive in this work. And then finally, my friends and family who make all this worth it. So thank you guys, and I'd be happy to answer any questions.
Thanks, Ron. So I think the first round of questions should come from the audience. So the audience being everybody who's not a committee member or anybody who's not from Bettis, we can take those questions later.
All right, I'm also going to enable the video too, so if you guys want to turn your video on, you can.
So I think if you want to ask a question, you just got to speak up because I don't know how to do it otherwise. No. Okay, if there's no questions from the audience, then I guess we'll move into the closed section. So, yeah, I guess if you could drop off. I don't know, Roman, do you have a way of expelling people you get rid of?
Yeah, I think I can boot everybody. Yeah.
You didn't give him a chance to clap there, Greg.
Yeah, we haven't figured out how to do that electronically very well. It comes off as a slow clap, which isn't really good.
Yeah, so I think I had it locked so that, oh wait, maybe I just did, never mind. All right.
That's one way to not have questions.
I thought I did, but I think it
Okay, it's
should have been fun. I wonder if Dakota can hear me across the hall. I'm pretty sure he's in his office.
No, I'm at my home right now.
Oh, okay. I heard somebody right across the hall as I was starting, and I thought it was getting in.
Oh, maybe someone broke in.
Okay, I think we're down to the committee, so I don't know what order you want to go, but maybe we should start with people from Madison. So Evan, did you have questions, or Louise?
Yeah, I have several. I could let Louise go first if you have some. You're on mute, I guess.
Louise, I think you're muted if you have questions. Uh-oh.
I'm okay. I read the pieces ahead of time.
Okay.
I saw Roman.
Several times, yeah. Thank you.
All right, Evan.
Yeah, I guess I'm guilty of not reading it enough. I actually have read it some, but I haven't had a lot of time recently. I do have a couple questions.
Yeah.
So one thing that really happened in this work is that you guys went in a little bit different direction than what we were initially thinking, which is good, and that happens all the time, and I'm all for it. But I'm curious if you, so one of the things that's changed is that the focus of the thermoreflectance has become more on the F-dry characteristic than it is on trying to characterize the instantaneous temperature. So I know you were able to get heat transfer coefficients more like average, a little bit time averaged, but do you think there is significant value in getting the instantaneous or trying to get a measure of the instantaneous, or do you think F-dry is really the way to go? I have an opinion, but I'd just like to hear yours.
So I think that they might be useful in different ways. So I think that using the F-dry and the time average heat transfer coefficient, it might give a better, I guess, depiction of the entire boiling crisis process. But if you're really interested in the physics that are occurring, I think the instantaneous measurement of the heat transfer coefficient would be more useful in understanding the actual physics of the heat transfer. And so that's definitely something that we're still interested in and still, obviously have to do. And I have data for heat transfer coefficient using the thermal reflectance signal from this study, actually, but it's during dryout. It gets a little noisy, obviously. And the values that I was getting for heat transfer coefficient were on average the exact same that I was getting for the time averaged heat transfer coefficient using the resistance network.
Okay, yeah, I guess from what I've observed, it seemed like F-dry is almost more useful, but I don't really know the answer. But I think when you can boil things down to something that is simpler to measure, sometimes that's more useful from a practical standpoint. But maybe, like you're saying, from the amount of detail you could get from an instantaneous measurement, maybe that would still really have value. My other question is kind of looking into the future a little. Do you foresee any problems in applying these techniques to the flow downstream of an obstruction? Like if you do these measurements in the next project in the region downstream of an obstruction, do you see any issues?
So no, there's nothing obvious, I guess, that I have thought. Working in the lab, of course, there's going to be issues. There's going to be things that arise and that I don't see at all coming. But right now, I don't think so. I think it should be relatively straightforward. I think as long as we have the The thermal reflectance or the laser reflectance slightly downstream from the obstruction, and the liquid film thickness. I mean, it would be nice to characterize the liquid film thickness both upstream and downstream of the obstruction. And so, with the addition of the camera, the second camera that we're getting, I think that we should be able to make measurements that accurately depict what's going on.
And just one more, I'll stop after this question, just one more in relation to this, but one of the things the path for going down is to try and measure the liquid film Reynolds number, the mass flow rate of the film sort of somewhat instantaneously. Instantaneously is not the right word, but over short windows of time averaging. And from what you learned in all this, do you see that, like you started to go into some of that by saying that the dryout really is affected by the loss of shear at the interface and whether you get something near a stalled film. The liquid film Reynolds number is a way of trying to get into characterizing that, but do you see that as really relevant, or I don't know, do you have thoughts on that liquid film Reynolds number issue?
Yeah, so actually, we just recently, within the last week or two, actually, we started throwing around this heat transfer model that's really only dependent on the liquid film thickness. And so if you're able to accurately characterize the liquid film Reynolds number using, if you define it as with the film thickness rather than the diameter of the entire tube. Some authors have the liquid only Reynolds number, they use the diameter of the entire tube, but I think if you define it using the liquid film thickness, then I think that the Reynolds number would be very useful, because then you can non-dimensionalize that equation, and I'm sure your Reynolds number is going to be one parameter, and then perhaps F dry or something like that could be another parameter, but I certainly do think that the liquid film Reynolds number will be useful. Does that answer your question?
Yeah. Oh, yeah. Yeah, we'll talk more later about it too. I'll stop.
Okay, thanks. Andre, did you have questions as well, or?
Oh,
Or is he
I don't
not?
think he's actually there.
He's not there. Okay. Oh, look, he's gone. That's good. Okay. So let's go to, I guess, Dakota. Did you have some questions you wanted to ask Roman?
Yeah. For in the future, if you try to do these time resolved temperature measurements, what do you estimate the time response you need? And what's the temperature resolution you would need?
So if we actually have done this work already for liquid phase, and I think I failed to actually put a calibration in here. I did. So we can accurately measure the temperature at the interface in liquid, or when there's liquid at the interface within an uncertainty of 0.1 Kelvin, and the response is near instantaneous. I mean, we can sample the measurement currently we sample the measurement at 2,000 hertz, but that's just because most of our instruments, sampling any higher than that, most of the instruments wouldn't actually give any sort of a better of a response. But the laser, we can sample that as high as we want. And so I think the time resolution that we're getting for the temperature measurement is good enough. And I also think that the uncertainty in the wall temperature with liquid is good right now. We're trying to do the same thing currently with vapor. So once the window dries out, we have another laser setup basically that tries to measure the wall temperature with just vapor at the interface. And currently that signal is a lot more noisy. There's a lot more uncertainty associated with the vapor side. And so we would like to get the uncertainty down to something, like within a few tenths of a Kelvin. But the resolution the time resolution for that wall temperature measurement is also really good. So it's very fast, near instantaneous.
But based on the dryout times and rewetting times, those are on kind of like tens of millisecond timescales. Is that right? Or?
Yeah. So the where do we go here? You guys can see my screen still, right?
Yeah.
Yeah, so most of the dryout events occur very, very quickly, especially at these low F dry. So when dryout first occurs, it is on the order of just, tens of milliseconds, hundreds of milliseconds. And then eventually for flows that are drying out repeatedly, these dryout events start to last much longer, where, you have near up to a second where it's fully dry, and then a big wave comes through and re-wet.
So does the temperature measurement have to be an optical measurement? Could it be is it possible to do like a resistance measurement, temperature measurement, using like a RTD or like a small thermocouple?
It is, yeah. So we actually do have small thermocouples. When I go back to the test section figure.
Yeah.
We do actually have, if you look here, so I have these four here are actually thermocouples that go into the Altem, and basically there's a slit in a plug, and the thermocouples are just really, really fine wires, and we just lay them in that slit, and then we've verified that they accurately measure the saturation temperature. And so there is thermocouples along the edge, but we don't want to put something on the glass that protrudes into the liquid film.
Right.
So we want the liquid film to be as stable as possible when we, or as, I'm not disrupted by anything in the apparatus.
And do you know how small is small enough? If you had like a thermocouple junction there, like.
Yeah, so it's on the order of microns. So so the liquid film thickness typically is on the order of like 50 microns, to 100 microns. And then when you're heating, it gets down smaller, like I said, 30, 40, 25, like really small. And so anything that's bigger than a few microns would disrupt the flow.
I see. And what's the current time constant of the thermocouples that you are using? Do you know that?
So the thermocouples within the test section respond. It's a slow response. It's within a second or two. The time lag for the exterior thermocouple is about 5 seconds, and that's associated with the diffusion constant through the window, or the diffusive time constant through the window. But the response of the thermocouples in the test section is not very good, but it's also not it's not totally necessary that it's very good, because really these thermocouples measure the saturation temperature, or measure the temperature, and then we compare that with the saturation temperature that we get from the absolute pressure that's measured here. So basically these all measure saturation temperature during two-phase flow.
Okay. Thank you. And I think I had another question, basically about the uncertainties you mentioned earlier. Where are the biggest uncertainties in your measurement coming from?
Yeah, so the biggest uncertainty actually comes from the heat losses. And I'm happy you brought this up, because I did put this in a table but took it out because I thought people would think it was boring. The biggest uncertainty comes from the heat losses. And so that's these regressed variables. Damn it, I didn't show. Hold on, here we go. There we go. So the regressed variables here, so this R sub Ts, that's the resistance associated with conducting through the Altem and then eventually convecting to the surroundings from the surface of the Altem, and then the natural convection on the exterior of the test section here. This is the largest source of uncertainty. And so these are like 10% of the value is the uncertainty here. However, for two-phase conditions, and this is due to a few reasons, but under two-phase conditions, about 99% of our heat input is actually transferred to the working fluid.
I see.
And so there's very little heat losses during two-phase experiments. And so therefore this makes the actual uncertainty on the heat transfer coefficient and the effective heat flux very, very small. For single-phase conditions, these become large.
What are the uncertainties for the single phase?
For the single phase conditions, so this, that's the one. There we go. So the uncertainty for the single phase condition. So here's the Nusselt number, and it's a non-dimensional heat transfer coefficient. It's about 10% of the heat transfer coefficient.
Okay.
Anything else, Dakota?
No, thank you, Roman. That was great.
Thank you.
So Franklin, I guess you're up.
Okay, good job, Roman. Actually, my top question was about the heat transfer coefficient and the fraction of heat that's lost versus going into the fluid. So I guess you've already answered my top question. Can you go to page 29? I was writing and trying to manage a child doing their online school at home, so it was a little...
I totally understand, absolutely.
It's a little interesting. So page 29, okay. Yeah, okay, normalized heat transfer coefficient versus... Yeah, just help me understand what H weighted is versus its 1 minus F dry.
So yeah, H weighted represents the heat transfer coefficient if it simply went from its value when it was wet to its value when it was dry.
Okay, so all right, I get it. Okay, all right. So what is the explanation for this? That's what I wanted to get to. What is the explanation for this increase right before, you get this sudden decrease? Is there a phenomenological explanation for that?
Yeah, so actually this goes back to that heat transfer model that I've been working on recently. And so if you break up the flow into a few different regimes and you break it up into basically wet, dry, and then you have the evaporating film region. So the evaporating film, the film thickness becomes very, very small. And so if you assume that the conduction length across, the entire temperature gradient happens across the liquid film, as the liquid film becomes very, very small, you have a big increase in heat transfer coefficient right before you dry out.
Okay,
when you're dry, only a few percent of the time, that increase that you get from being very, very thin is enough to make up for the decrease that you get for the time that you spend dry.
Yeah, to more than make up for it. And then when that dry time starts to be a significant fraction, then you see this decrease. Okay, that makes sense.
Exactly. Yep.
All right. I think that's all I had. I was really interested in your sources of error. So in the case where you have this error associated with the heat flux going to the surroundings is only 1%, is that still the dominant uncertainty?
Yeah, the heat loss is so. So the dominating uncertainty of the heat input into the refrigerant is this pressure transducer here. So this absolute pressure transducer here is the dominating uncertainty for the heat input into the refrigerant. So the refrigerant characteristics or the refrigerant properties that are calculated using the saturation temperature and pressure, that's where the uncertainty comes from here.
But as far as the uncertainty on the heater input into the wall, even though it's still 99% going into the fluid, that's still the biggest uncertainty there.
Yep.
All right. Okay, that's all I had.
Okay. I don't know, Argenthal, did you have questions that occurred to you?
And I've had a couple of years to
That's kind of what I figured. I thought I'd give you and Chris a chance. Chris, did you want to say anything?
Yeah, just when you calculated the times, the time between dryouts based on fluid density, film thickness, velocities, blah, blah, blah.
Yeah.
I forget the slide number. Could you just talk about that a little bit more? Because that's remarkable that this predicts a quarter of a second and the data shows a quarter of a second. Yeah. So where is this delta rho, delta enthalpy over Q dot? Where does that come from?
So this, if you just basically using this control volume and you just perform an energy balance and calculate the time it would take to vaporize the entire control volume of liquid, this is where that time comes from. Okay. And so basically, what happens here is that after, and especially in situations where you're drying out repeatedly, you have a wave come through, but all of the fluid in the wake of the wave is essentially stationary, and therefore it just vaporizes. And the time it takes for it to vaporize is calculated here and is shown here.
That's
Was that a softball?
No, that wasn't, because this is, I must have missed our meeting. I missed a lot of meetings this fall, and I must have missed that one. But that's very clever to just. I mean, it's a simple thermal problem there, right?
Right.
Maybe it's a little tricky thermal problem.
It's my favorite. That's my favorite result of this piece.
Yeah, right.
Okay. So I don't know how to kick you out. And so
I just
you can
leave, I
leave.
guess.
Yeah.
Do you want me to come back, or should I just leave indefinitely?
I'm gonna need to come back, but I'm also gonna need you to leave. So I don't know how to do that. So maybe if you leave, and then I'll email you right away, and then you can come back when I email you. Does that sound
okay?
Yeah.
Do you know about how? Like, do I got time to go to the bathroom?
Probably not, actually. I don't think so.
All right, thank you.
Yeah. Okay. Any, I guess, concerns or, I mean, from my perspective, you become just blown over by it.
So I would ask this question, or maybe make this observation, that I've seen a bunch of master's defenses, a bunch of PhD defenses, and a bunch of research presentations by faculty candidates. And if I had to qualify this, or if I had to categorize this, it would go in the other end of the category, right?
Yeah.
I agree. I'm biased. I've been working with Roman for 8 years, but that was pretty damn good.
Yeah, he's real good. It's been fun to watch, actually.
Is he sticking around? He's going to stay around for a PhD?
Yeah.
Okay. Right.
Yeah.
So he's staying in on our projects, or do you guys have other plans?
No, he's staying on.
We get to keep Evans.
Okay. So we need to get our act together on getting really well-defined longer-term projects going.
Well, I think yeah. Go ahead.
Yeah, it'll be an interesting bifurcation between what Roman does and what Jason does, and but I think we should take a week, give Roman a week to kind of recover, and then let's have a much longer discussion about what direction we're going. Yeah, because we still have to add the pulses back into this. We have to figure out the obstruction stuff. There's a lot of work to do.
Yeah. But I just want it to be well defined.
Yeah, right.
I didn't realize he was staying, so that's very good.
Oh yeah.
I think it's nice that he's done all this work in a straightforward situation, because I think most of it's going to transfer pretty directly to if you add a pulses or if you add an obstruction. I think the techniques will transfer pretty well. So okay, Franklin or Dakota, anything else? Otherwise,
not for me. It was good.
Okay, I'm going to ask him to come back. If I can do that. I'm so looking forward to having people in one room again. I think he's.
It's a much shorter drive for Evan this way, though.
In this weather, you guys aren't having a snow. Maybe we're having a big snow today.
Yeah, we got that 2 days ago. It was great.
Well, I'll try again.
Yeah, I thought you could get back in the same way.
Huh. Well, okay. I mean, he'll show up here in a second. Just in terms of the logistics of getting these things signed, I think. Is he back now?
Yeah, he's back. Okay. Change topic.
Oh, okay. Congratulations, Roman. Your reward is 3 more years of paid. So.
Thank you.
So you have a warrant and that silly learning objective thing, right?
Yeah.
Yeah, okay. So If you send that to me, I'll start it circulating around, and we'll get it back to you with the right signatures.
Awesome.
Is this electronic, Greg? Because you can use DocuSign. It's a whole lot easier. Everybody signs it.
Well, just draw it.
We can try that.
Just put your signature on the PDF. Just with your.
Yeah, I mean, you can do that, but the DocuSign means that you don't have to circulate it around. Everybody can just go in there and sign it, and then it's done. It's the easiest way to do it. But if you don't do it that way, that's fine too. I'm just saying you can do it that way. Many of my students have done that, and it just makes it so much easier.
Okay. We may do that depending on how technologically savvy we end up being. Otherwise, we'll just do you can add your signature.
Pretty easy. All of my prelim students did it this year.
Okay.
Easily.
We'll give it a shot. It's make it sound so easy, but
I didn't actually.
Yeah, I was gonna say it's easy for your students to. All right. Thanks a lot, Roman. I thought that was great.
Yeah, it was very good.
Yeah. So.
Thank you.
And thanks Dakota, Franklin, and everybody from Bettis for coming. So.
Yeah, thank you guys for joining us.
Great job, Roman. It was a good one.
All right, I'm gonna head out to another one of these. So.
I'm gonna send those forms over to you. It's just the degree request, and then what is this? Is it just the one form or two forms?
There should be two, or is that for PhD theses that there's two?
I mean, that thing meet, exceed, or didn't meet that one?
Yeah, is that for the masters or just?
I think that might be for. I think that maybe that's just PhD.
Okay, well, just send me the other one, and if you submit it and then yell at you, we can do the other one too. So.
All right.
Yeah, you do the one form, and then I think the cover page, just Greg has to sign it. I don't think we all have to sign it on a master's. The cover page of the piece, it's only one signature for masters, I think.
Yeah, I think on this cover page, we're going to have Arkansas and Chris sign.
Okay.
They were massively important to him.
And then do I need to produce that cover page, or do you have like a template?
So it's just going to be your with your title on it.
So like my title page, and then do you want me to like make lines on there? Like what do you?
I'll send you a template.
Okay.
Or just look at any other thesis. Just look at that, and you'll see right there how they did it. So. Yeah. Okay.
All right. Thank you.
All right. Thanks, everybody. All right.
So,
happy holidays.
Yes, well, so Evan and Louise, should we just via email? Oh, we lost Louise. Oh no, everybody's moving around too fast. We'll just via email set up a time to kind of regroup and move forward.
Sounds good.
Okay. Yeah.
I'm actually going to be available a lot over the next couple of weeks. So
yeah, me too.
I don't know if you guys are on vacation or be around, but if anything over the next couple of weeks, I can definitely participate.
Okay.
I'm out next week.
You're out next week, please?
I'm out, but I'll be traveling. Ill advised.
Traveling? That's like wearing fur.
Sorry?
That's like wearing fur.
Yeah. But I should be available like the first week in January, or if we want to do it on Monday next week, if that's enough time for Roman to regroup.
Yeah, for sure.
So next Monday, we'll shoot for something next Monday then? Is that good for you too, Evan?
Sure, yeah.
Or Arkansas will good for you too, because you're still working on grades probably, right? As am I.
Yeah, I should be fine. I think the date for Monday night. And they'll help me, they say. I just got an email this morning. They said they'll help me with grades. So.
Excellent. Yeah. Right.
Yeah, I got that email.
Inside joke. We'll explain that. We'll explain that on Monday. All right. So sweet. Awesome job, Roman.
Thank you.
Congratulations.
Bye.
Bye.
Thank you.
Hey, Roman, who is taller than Roman?
Yeah, I was wondering who that was too.
That's my little brother.
All right.
He is taller than me, but he is the little brother.
All right.
He'll always be the little brother.
Yeah, that's funny.
My little brother could kick my ass starting at about age 18, so that's I'm in the same boat.
Oh, I'd still kick his ass. He knows that. He's just taller.
All right.
All right. Thank you guys so much.
All right, you guys take care.
Congrats.
Take care.